examine the function g of x equals ln of 4 minus x squared for the following properties and use that info to sketch a graph. We're going to start with the domain, and this one's a little bit more interesting domain-wise because we have a polynomial inside a logarithm. We know that a logarithmic function is only defined for positive numbers, so the inside of that, 4 minus x squared, has to be greater than 0 for this to be defined. That is interesting. If we add x squared to both sides, this gives us 4 is greater than x squared. And sometimes it's a little easier to flip things around and think about x squared is less than 4. We know that x squared is equal to 4 when x is 2 or negative 2. If we want to know when it's less than 4, we've got to look in between 2 and negative 2. Those are the values of x where x squared is going to be less than 4. Right? 0 squared is less than 4, 1 squared is less than 4, negative 1 squared is less than 4. So really the domain here is going to be from negative 2 to 2. So interesting. This is quite different from some of the other examples that we've looked at. All right. Let's talk about intercepts. For the y-intercept, that's going to happen when x is 0. When x is 0, the inside is just going to be 4, and so we're going to have ln of 4 as our y-intercept. So y-intercept is going to be at 0, ln of 4. We'll use a calculator to approximate that in a little bit when we actually plot points. We can leave that for now, though. If we want any x-intercepts, that's going to happen when the function value is equal to 0. So it's going to happen when ln of 4 minus x squared is equal to 0. This is a logarithmic equation because the variable's inside the logarithm. The way that we can solve this is by rewriting it in exponential form. So the base here is e because it's a natural logarithm. So in exponential form, this is going to be e to the 0 equals 4 minus x squared. E to the 0 is equal to 1. So we have 1 equals 4 minus x squared. If we subtract 1 from both sides and then add x squared to both sides to get that x squared alone, that's going to give us x squared equals 3. And so taking the square root, we're going to have plus or minus the square root of 3. So our x-intercepts are going to be at plus or minus the square root of 3, 0. Interesting. For symmetry, we are going to have symmetry about the y-axis because, again, we've got this x squared here. It doesn't matter if x is positive or negative. When we square it, we're going to end up with the same thing. So we will have some symmetry about the y-axis. And then for asymptotes, we know that the logarithmic function has a vertical asymptote as we're getting near its endpoint when the inside is equal to 0. And the inside of this, the argument is equal to 0, specifically when x is 2 or negative 2. And so as we're approaching 2 or negative 2, the inside is approaching 0, and we know that the natural log function has a vertical asymptote when the inside is approaching 0. So that means we're going to have vertical asymptotes at x equals plus or minus 2. So we've got 2 vertical asymptotes here. Now, for the intervals of increase and decrease, we're going to need a derivative. So we need g prime of x. And we're going to have to use the chain rule here because we have a composition of functions. The derivative of the outer function, ln of u, is 1 over u. So that's going to be 1 over 4 minus x squared. But then we need to multiply by the derivative of the inside, which is going to be negative 2x. So our derivative is going to be negative 2x over 4 minus x squared. The critical numbers here are actually, we've got the endpoints at -2 and 2. The denominator is going to be 0, so that'll be undefined. Those are outside of our domain, but they're still the endpoints of our domain, so we'll consider those. But then also our numerator is 0 when x is 0, so that's also going to give us a critical number. We'll have a critical number at 0, and then the ends of our domain at -2 and 2. Now, -2x is going to be negative when x is positive, and positive when x is negative. And 4 minus x squared is going to be positive in each of these intervals. We can just plug in any value for x and see that that is the case. And so our derivative is going to end up being positive and negative. So we are increasing and then decreasing. And so we have a local max at 0. And when x equals 0, y is ln of 4. That's already our y-intercept. So that's also going to give us a local maximum, which is really convenient. Again, I am going to be lazy, and I'm going to just give you the second derivative and ask you to make sure you can calculate this on your own. It is a rational function, the first derivative, and so when we differentiate that, we use the quotient rule. We will end up with -8 minus 2x squared all over 4 minus x squared, quantity squared. The denominator is always going to be positive, and the numerator is always going to be negative. So this is always going to be negative on our domain. This is always going to be less than 0, which means it's always concave downward. We don't even need to make a sign chart there. And now we've got enough information that we can start sketching this graph. We know that we have a y-intercept of 0, ln of 4, which is about 1.39. So it's going to be a little bit less than 1.5. And we know that we have our x-intercepts at plus or minus root 3. That's about 1.7. So we'll have our x-intercepts at positive and negative about 1.7. We said that we had asymptotes, vertical asymptotes, at plus or minus 2. So we can draw those in here as dashed lines. And then if we looked at our intervals of increase and decrease, we're going to be increasing up to 0 and then decreasing. We are concave downward everywhere. This is, I think, not too difficult to draw. If we start with our local maximum and move to the right, we are decreasing and we are concave downward, and we are asymptotically approaching x equals 2. We have symmetry, and as we go right to left, we're going to go downward, and our graph is going to be concave downward and asymptotic. And we're going to have something that looks like this, and that's the whole graph.